So see, even though I have given the title to be gas hydrate and all blah blah blah, but I would like to focus little bit more on how a chemistry student thinks and how an engineering student thinks, and why it is important for us to have a good blend of these two. Okay, so I will talk about the hydrates initially, but later on I will go into little bit of an application and try to explain you how some of these things are basically utilized in industry and why it is important to think in that particular direction. Okay, so today we will try to understand hydrates. I don't know how much time do I have, that much you will tell me. So it's 1 hour plus 15 minutes. Okay, 1 hour plus 15 minutes, 1 hour plus 15 minutes is what I have, I should know that. Okay, so if you talk about hydrates, I will give you a little bit of more detail later on, but as I was telling you, I am an engineer, so I bring the application first, fundamentals will come later. Okay, so first time when during industrial revolution, engines were already running, lot of engines were designed, it was already running, no one understood how it run. The efficiencies they were not able to improve. So later they brought the theory behind why we are not able to improve the efficiency and all. So it's that application which comes first. And once you have understood what is the application, then the kind of knowledge which is needed to achieve that kind of application goes into that. Okay. So I think it's always important for us to understand where the application will be, and based on that we will understand enough so that I'll be able to utilize it for that particular application. So this is what I'll try to do today. So gas hydrates are crystalline molecules, we will talk about it, but then where actually it gets applied is what I'll start telling you first. This is where the initial studies of gas hydrate happened. Flow assurance in oil and gas pipelines, typically oil and gas pipelines comes from deep down under the earth. There will be oil, crude oil, there will be gases, natural gas, for example methane, ethane, propane and all. Along with that, huge amount of dirt comes out. Okay, this is why it is called crude. So all of these comes out from under the earth, which is quite far. If you are onshore, offshore, depending upon where is the field. If it's offshore, it could be 4 kilometers, 5 kilometers pipeline through which these things will come out. Okay. So how exactly it comes out? There is a large pressure built under the earth, it's like a straw. If there is something which is kept at high pressure, I drill a hole, it will ooze out from there. Exactly that's how oil is being produced. These oils are there under some pressure because there is a lot of gas also around it. So that will create that pressure. So you just need to draw a hole there. And once you have drilled a hole, since there is high pressure inside, it will come out. This is exactly what we do when we drill oil and gas for oil and gas. The pipeline goes in, it goes to the location where there is oil and gas available. Okay. So early days, these oil and gas used to be in the form of a pool of liquid oil and gas there. We have consumed most of that kind of oil and gas now. Now the oil and gas which is available is pretty much within the pores, okay, of the rocks. So even though there is high pressure, it will not come out that easily. But those days it used to come out that easily with very high pressure. There used to be certain advantage those days is that water used to be very limited in these oil and gas fields. Today we have oil and gas fields which has plenty of water as well. So that creates another layer of problem, but I'll explain you. I know I will go all different direction. You will have to be with me. If you lose me, then you bring me back. Okay, I will also digress a bit. But if you are not getting something, raise your hands. We will try to understand it. Again, it's in a story. Don't try to write anything. Listen to me. That's all you have to do. If you want the notes, I will share the notes. That's not a problem. So what we are trying to do, the story is that there is someone sitting down the earth. We are trying to bring him or her out from there. Okay. So this him or her is that oil and gas we are talking about. And then it comes with lot of dirt, it comes with lot of water and everything is there. It's a very complex mixture. You will not understand. You'll try to understand, you will not be able to understand anything there. Okay. Because as a chemistry, we look at one molecule, we see how it interacts and all. There are 100 different molecules. How we will look into that? It's not possible. So you will have to have a bird eye view. What is the bird eye view over here? Is that we have oil and gas there. It's coming out from this pipeline. It basically means this pipeline is going to be pressurized with oil and gas. Okay. This pipeline is going to have oil, it's going to have gas, it's going to have water. So what all we have now? We have high pressure, we have oil, we have gas, we have water, and with these, what was not known those days, that with a particular gas and water, ice like crystals form even at temperature above 0 degree centigrade. Where you have seen ice? You have also mostly seen ice when water crystallizes when you go below 0 degree centigrade. Okay, if it's an heterogeneous nucleation, you will be able to see it at 0 degrees, -1 degrees. When it's homogeneous nucleation, you will have to go really low, -30 or something. That is when you will see the crystals growing. Till that time, it will not grow. But those days, it was not known that ice-like crystals can form even above 0 degree centigrade if you have a gas present along with water. Okay, those were the days, that is early 1950s. People knew that hydrates exist, but in industry they were not bothered about. Academicians knew that hydrate can form, but in industry they were not bothered about. So what happened actually those days? Huge amount of those were days where when people slowly realized that coal creates lot of mess. Ash was the bigger problem. CO2 was not a problem. Ash was a bigger problem. So they were swiftly moving from coal, which is solid, and ash, the byproduct, is also solid. They moved to oil because when it burns, nothing is left behind. Pretty much whatever is left behind is in gaseous form, so it will go to the atmosphere. So huge amount of all the requirement which were initially met by coal were being shifted to oil. So oil and gas exploration was going in big way, and people were digging for oil and gas, going really deep under the sea. And this is when they saw this problem, that their pipeline used to get clogged by this crystalline hydrates forming on the side of the wall. Okay, and what will happen because of that? You will see that the flow. What is the flow we are talking about? The oil and gas which flows from a high pressure, which is deep down, to the low pressure on earth, is somehow getting obstructed. This is why this name came. The flow is getting obstructed, so we need to ensure flow assurance. Okay, so what exactly people started doing? They looked into a lot of chemistry about it. They figured out that, okay, this is not an ice which is forming, it's hydrate which forms, which can form even at 5 degrees, it can form even at 10 degrees if you have the right pressure. So how do we avoid it? So this is when they basically started working into additives. What are these additives? Why hydrate forms? So let's start from there. Now, why hydrate forms? Why ice forms? When we have water molecules at room temperature, they have some thermal fluctuation. Each water molecule has some thermal fluctuation. They try to form this hydrogen bonding, but because of the thermal fluctuation, that hydrogen bonding does not form. One water molecule is fluctuating over here, one water molecule is fluctuating over here, and they are not able to find that optimum distance where the attraction is going to be sufficiently large that they will form this bond. When that will happen? If I reduce the temperature, the thermal fluctuation comes down, and then they find enough distance that they would start forming this bond, and that happens roughly at 4 degrees centigrade, and then you will see at around 0 degrees, you will see water crystallizes into ice. Okay, this is what we know of water crystallizing into ice. These hydrogen bonds form, and then we get a beautiful crystal coming out of it, and we see there is a phase separation. Solid will get separated out with liquid water, which will ultimately form, all of the water will get converted into solid ice if my temperature remains below 0. If my temperature is somewhere above 0, then there will be an equilibrium which will be attained, and all that we know about. Okay. When a gas is present there, what happens? If I am able to, instead of reducing the temperature to minimize the thermal fluctuation, if I am going to pressurize with a gas, if I am pressurizing a molecule with a gas, what happens? There is not enough space for this molecule to fluctuate. So when I am pressurizing with a gas like methane or carbon dioxide or something else, in this particular case, you see these thermal fluctuations are minimized. And when this gets minimized, this crystalline structure might form with the same hydrogen bonding even before 0 or at higher temperature than 0 degree centigrade. Okay, and this is why hydrate forms. So if I am, so with this analogy, if I am having more pressure of gas, hydrate will form at higher temperature. When we have no pressure of any gas, then this crystallization will happen only at 0 degree centigrade. So now you see, since this system had water, it had a gas, it started crystallizing out even at 5 degrees. It may even crystallize out at 10 degrees, and if it crystallizes out, then the flow gets obstructed. Down that end, we have very high pressure. Up over here, we have low pressure. So we expect what the businesses would expect. Maximum amount of oil should come out from this pipeline. Okay, that is how they will make more money. But if that pipeline starts shrinking, why it will shrink? Because the crystals are forming on the walls of the pipeline. The metal wall is going to be slightly cooler compared to the liquid which is coming out. So where it will crystallize? It will crystallize at the temperature of the wall where it is slightly cooler, where the thermal fluctuation is the minimum. So it will crystallize out there, nucleate there, crystallize out, and slowly it will grow. And if this is the pipeline, and if it's growing, so it will become like this. So your pipelines are becoming narrower, 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 and then ultimately you will see that some location it gets completely blocked, and it becomes a challenge. What is the challenge it will become? I will show you if we have a marker here. Now, please understand, this is not going to be a straight pipeline. Let's say somewhere over here, this is the pool of the oil we are talking about. Okay, and let's say this is the pipeline we are talking about. I have drawn it poorly, but it's a nice pipeline, not larger, smaller dia and all. But let's say this is where it has completely got blocked. Somehow the crystal over here has really become that growth has become so fast for some reason that it has completely blocked this out. Now what do I have? I have a high pressure over here, I have a low pressure over here. Okay. So what typically you will do, something has got blocked. So what they will do, they will bring a hot torch which goes inside the sea and will start heating this portion. Once you heat it, what will happen? These things will melt. So what they are doing, they are trying to be a good intention that the blocked pipeline should get open. So now this has melted, and this is high pressure, and this is, just imagine a big block of ice. What will happen? What do you think will happen to this? Yes, this will get, as soon as it loosens from here, it's very high pressure, it's very low pressure, it will go, and where it will go? Will it turn here? It can't. So it will directly go and hit it, and it will break. And as soon as it breaks, now you are inside the sea. How you plug it? It's a big challenge. Okay, it basically means the entire oil will start getting now in the sea. It's going to be a big mess. You don't want that to happen. Okay, this is why they thought, okay, and it happened. Many places this happened. So what they started doing, they started giving along with these pipeline, when they basically do different kind of, they will have to stimulate these wells many a times. They will have to supply some liquid from outside. They do all kind of things. So what they started doing, they started adding some additive. What these additives should be now? How the hydrates were forming? Two water molecules were coming together to form hydrogen bond. So what kind of additive I should use if I don't want this to form? Some molecule which will preferentially interact with water rather than two water molecule interacting with each other and forming this bonding. I would add a molecule which will preferentially interact with water. So that means I am not allowing two water molecules to come together and interact. What is one such molecule which comes to your mind? Let's say alcohol. Okay, we can have a salt, NaCl. There are certain advantages, disadvantages of all these molecules. Ultimately, the idea here was to add some of these molecules in the pipeline so that this clogging of pipeline can be reduced to an extent that the water molecule which comes out from here, by the time it comes out from here, it does not get an opportunity to plug the pipeline. Okay, so that was the first instance when these are high value, every day millions of dollars is made. Okay, so Industry had lot of money. So they started funding people in academia to do this kind of research, which will allow them to basically ensure flow assurance. So this is where all the money for this research came. Fundamentals started building over there. What kind of hydrates are forming? Is there only one kind of hydrate which may form? Different gases forms hydrate at different temperature and pressure conditions. Whether one kind of additive which works here may also work in some other location. What kind of delta T we'll have to operate with? All kind of challenges were there. Okay, so that research basically funded significant amount of money into this, and this is where this research actually developed. This is the story of 50s, 60s. Later in 70s and 80s in Russia, people figured out that under the seabed, there is significantly large amount of methane hydrate which exists. Now, if you remember what we talked about, why hydrates would form? Hydrates would form at when water molecules would come together and form the hydrogen bonding. Under the seabed, typically we don't have 0 degrees, but we have temperature very close to 0 degrees, 4 degrees, 5 degrees, 6 degrees. Why? Because the sunshine does not go there. The thermal heat also does not come to, at the bed. If you go deeper down, then you will see that kind of a thermal heat. Subhadeep, I am in a class, I will call you later, okay? Thanks. So, deep down you will not have that kind of heat. The temperature is not 0, but it is around 4, 5, 6, 7 depending upon at how much depth you are from the surface of the sea. So, you have low temperature. Now, we all know that methane reservoirs are there all around. It basically means there is plenty of methane is also available, which is continuously coming out. So, what are the molecules we need for hydrates to grow? We need water, which is there. We need methane, which is there. We need the right temperature and pressure conditions, which is there. Temperature we talked about, and the water column will create the pressure. So, we have all the 4 ingredients. It basically means technically there should be lot of such hydrates under the seabed, and this is what Russians found out. So, this is when they started looking into how do we use this hydrate as a source of natural gas. Even today we know that there are plenty of methane hydrates or natural gas hydrates which are under the seabed, but we don't exploit it mainly because it's expensive to exploit it. If you have something kept in a ball, you will go and exploit that first. No, this is in a different kind of a matrix. Okay, if I have to exploit this, what do I need to do? See, when it is methane gas present as a gas, we'll put a straw and it will come out. Okay, but if this methane is present inside something, we'll have to break it first. Okay, we will talk about it. So, it basically means energy, this is an energy intensive process. So, but this is one research area which has funded significant amount of money in this research. How do you, what do you understand by hydrate, how it works, how do you dissociate it? You see, in this particular case, it was how do you ensure that it does not form? In this particular case, what was the research on? How do you dissociate it? It has already formed. Nature has formed it for millions of years. Okay, it is stable. How do I dissociate it? It's a dissociation kinetics is what one has to now study. Okay, this once it has already formed, it's very dangerous. We talked about it. So here, what were the argument that we will not allow it to form. So we will use a inhibitor which will inhibit the nucleation of hydrate crystal. We will use an inhibitor which will inhibit the growth of hydrate crystal. We will use an inhibitor which will not allow two hydrate crystal to come together and become a larger crystal. How do you do that? I put in a small crystal, once it has nucleated, I add an additive which has a long tail. The water loving part will go and get attached on that crystal. The water hating part, this is the tail, will not allow the other molecule to come because of the steric hindrance. You see, that is how you basically design your molecules in some of these cases. But the same molecule may not work over there because the hydrates are already formed. What the tail will do? Nothing much. Okay, so there you need a different kind of additive. What kind of additive you may need? You may need an additive which will go and sit on the surface and will start creating case defects. How it will happen? So this is a different kind of research which is needed. Doing the same kind of research, if you say, oh, I am working on gas hydrate, but no, here we are doing something differently compared to what we are needed to do over here. Okay. Now, these things were having significantly large amount of money, which had a significant application, which was available, which was visible. Some of these were making money, some of these were potentially would have made money if we do it properly. Okay, so this is why huge amount of money came. Now there was another class of research which was actually developing when I started doing my PhD, and this is where I did my PhD on. Okay, this is in the story of 2004, long back, some 20 years back. So those days people were knowing these hydrates are there, mostly they were studying for it. So we basically, when we started our PhD, the project was on how do we basically ensure growth of hydrate to separate two gases. Okay, we were by now knowing that hydrates of different gases forms at different temperature and pressure condition. Okay, so now if I have a mixture of two gas, if I am going to form a hydrate, which of these two gas will go into the hydrate phase? Because if I am able to do that, I will be able to separate the gas. Okay, say for example, I have a mixture of carbon dioxide and nitrogen. Both are gas. They are intermixed with each other. In this room, we have one molecule of CO2 for every 2500 molecules of oxygen and nitrogen. Okay, that is roughly 400 ppm we talk about. Okay, it basically means if I have to capture that CO2 molecule from this, how do I do? I'll have to somehow put this CO2 molecule in these hydrate cages so that a nitrogen and oxygen should not go in, then I'll be able to separate it out. That was the project which we started doing. So that basically means I'll move on now. I have already discussed enough. So gas separation could be one approach. Now if I am able to store methane in this kind of hydrate, it can become a storage and transportation. How do I store and transport methane right now? Either I pressurize it so that it is at higher pressure, large amount of methane can be transported and stored at the same time, or I liquefy it. But if I have to liquefy it, I'll have to go to really low temperature. If I have to pressurize it, I have to go to really high pressure. Instead of that, if I can convert that into a hydrate, I don't have to really go to really low temperature or go to really high pressure. Somewhere in between, I'll be able to now transport it. So it could be a way to store and transport hydrogen or methane or a mixture of hydrogen and methane. So that is a possibility. Desalination is another such example. Again, now this is a very different topic. Here we are not bothered about what gas is going in, which gas will form hydrate. What we are bothered about? Let's now assume a water which is contaminated with whatever comes to your mind. Let's start with contaminated with some salt. I have seawater. Okay, how do you separate seawater? What do you do? Right now, if I have to separate, I have to desalinate seawater. What do you do? How do you desalinate seawater? Evaporator is one option. There is other better option. What we typically do? Reverse osmosis. Okay, we do reverse osmosis. We utilize the chemical potential difference and then we try to separate out the pure water from the impure water. Now, hydrates can do exactly the same. Reverse osmosis requires you to go to some pressure of 40-50 bar. Okay, it requires you to have a membrane, which is polymeric membrane. It basically means a membrane has to be synthesized. This has to be recycled or has to be sent into the landfill. So it's not very sustainable. On the other hand, if I am going to form hydrate from this saline water, what do I need to do? I can use a gas which will form hydrate. Hydrate will be formed with what? With the water molecule in this solution, not with the salt molecule. So when hydrate forms, what will happen? I will be able to separate the liquid from the solid. And if I have separated out the solid is a hydrate which will automatically dissociate at room temperature and pressure. So I will get what? Pure water once it has dissociated. So this is probably a novel approach by which you are basically separating out a pure water from impure water. Okay, it could be salt, it could be a color like dye, pigment, it could be effluent which has many other harmful chemicals in it, NaOH, HCl, anything could be there. I should be able to do exactly the same for taking out the pure water from the impure water. Okay, by using a hydrate former which is a gas. If I am using a gas for hydrate to grow, it will form hydrate, it will get solidified, and we can separate it out by centrifuging it. You do a lot of research where a solid and liquid is separated out by centrifuge. So you separate out the solid, and once you have separated out the solid, you release the pressure of that particular gas. Release the pressure means take out the gas so that you can use the gas for the next cycle, and whatever you will be left with will be pure water, because chemistry wise only the pure water will form this hydrogen bonding with other pure water molecule, and once it is all pure solid crystal, I have separated it out, I will be able to get pure water, and I have separated the impurity from the pure water. So that basically mean that it could be desalination. Now there is another application which is called refrigeration. Now when I am going to basically form something, when hydrate forms, what happens? Bond forms. Multiple hydrogen bonding forms. Millions of hydrogen bond happens between water molecule. When bond forms, what happens to the system? It goes to lower energy level. It basically means it will become an exothermic process. So if I am able to take out all the heat during hydrate growth by, let's assume, by supplying energy during the sunshine hours. Why sunshine hours? This is where the engineering comes. Why sunshine hours? During the sunshine hours, I can have solar panels producing electricity which comes virtually at free. Okay, so I use all this energy during the sunshine hours. I produce a lot of energy during the sunshine hours. The energy which I need for that 6 hours I consume, but the energy which I have produced in extra, I use all that energy to form hydrate from water. What I have done? I have basically stored that energy into bonded water molecule. Now when I am going to break that water hydrogen bond, what will happen? When it formed, energy was released. When it will break, what will happen? It will cool down. So all my refrigeration need of the building, of the community can be taken care by that, because if I have stored hydrate at 5 degrees centigrade and once I start dissociating it at that temperature will keep going down. So if I am going to have a temperature of 1 degrees, 2 degrees for all the time throughout the night, I will be able to cool the entire facility. This is what is called district cooling or refrigeration. So you see, if you are going to look into hydrates from a chemistry point of view, what you are doing? You are looking into how the water molecules are interacting, how the gases are interacting with that, how the crystals will form, what kind of additives will enhance the rate of hydrate growth. For example, in this case, when I am going to use gas separation, what do I need? I want water to get converted into hydrate very fast. Okay, it basically means I need an additive which has to enhance the rate of hydrate growth. Whereas when I am doing flow assurance, what do I need? I need an additive which will inhibit the rate of hydrate growth. So you see, two different application, two different kind of research is needed, but the fundamentals still remains the same. How the hydrates grow, what are the properties of hydrates. So with this background, let me now go little deep. This was kind of a broad understanding why we do this. Once we know why we do this, then we'll go into why we do this. So let's take an example, but let's not go into this. This I will come again. These slides will be there again. Don't worry. I'll go to the hydrate part first. So if you see here, what I wanted to tell you is that if I have to go for CO2 capture application, I did tell you about the gas separation. I gave you an example of mixture of CO2 and nitrogen. So when we talk about CO2 capture, when we talk about net zero, we talk about CO2 capture, utilization, sequestration. So the first step is CO2 capture. What exactly is this CO2 capture? The CO2 capture is basically, technically means I am separating carbon dioxide from other gases. Why do I need to separate? That also I will discuss later. It's there. I don't have the time though, but I will discuss quickly. So the point I am trying to make is that depending upon the requirement, we may go for different kind of CO2 capture processes. One could be a physical absorption process, one could be cryogenic distillation, could be membrane diffusion, could be chemical absorption. And if we talk about physical absorption process, hydrate based gas separation process comes over here. I will try to basically give you a small understanding about what exactly is this all about. These are hydrates. What are the hydrates? As I was telling you, it's very much similar to ice crystals. If you have in one hand ice crystals And in the other hand, if you have a hydrate crystal, physically there is no difference at all. You will not be able to separate or identify hydrate from ice. They exactly look the same because same hydrogen bonded water molecule. And do you think gases are visible? Gases are not visible. So even if inside the cage, if there is a guest molecule in form of a methane or carbon dioxide, you will not be able to see the difference. How you will determine which one of these two are hydrates? When you bring it closer to your ears, you will be seeing one of the hand, it will keep making popping sound, because these gas hydrates will not be stable. You are at room temperature, you are at atmospheric pressure. So these hydrates you have synthesized at high pressure, at low temperature. So you have synthesized, you have brought the crystal out, but then when you bring it closer to your ears, you will see that it dissociates, continuously dissociates. You will see the pop, pop coming out, methane will keep coming out, or CO2 gas which is inside will keep coming out, and you will see, you will hear it. You will put it in water, you will see all the gases comes out, and you will see a bubble of gas coming out of it. So this is how you basically differentiate, but physically there is no difference unless until I do a spectroscopic analysis. Okay, this is where there will be difference. We will talk about that. So if you see, it's very similar to ice crystals which are hydrogen bonded water molecule. The only difference is that these cages are bigger in size. These cages are bigger in size, and these are only stable when you have a guest inside. If you don't have a guest inside, these cages will collapse, or it will require you to go to even a lower temperature for this new type of cages to form, which we know as ice. Okay. So these are the hydrate cages where you have this guest sitting inside. You see, this is methane, 1 carbon and 4 hydrogen, which is depicted over there. It basically means this is one of these cages contains methane, and outside of this cage is hydrogen bonded water molecule. Now, if you look closer, you see this is 1, 2, 3, 4, 5. This is 1, 2, 3, 4, 5. It basically means there are certain features into these cages. These features are very much similar to ice. If you know those who works on ice, or you are little bit aware of it, there are different structures of ice. You can have cubic ice, you can have hexagonal ice, you can have amorphous ice, all kind of ice are there. Similarly, when we talk about hydrates, different kind of hydrates form, and it gets determined by the shape and the size of the guest molecule which fits in there. Okay, we will talk about in little detail, but what you see over here, gas hydrates are frequently encountered under seabed, and it can also be synthesized in the lab. I can synthesize hydrates in lab of multiple different structures. There are many structures. We typically don't talk about all those structures. We talk about few structures out of those which are available in nature, but in lab you can create many different kind of structures. Okay, we'll talk about it. But what exactly is this structure of hydrate is all about? Why we are going to basically study this? Why as an engineer I should be bothered about it? Because as an engineer I am supposed to find a solution to a problem which exists. The problem which exists we talked about is a gas mixture coming out from the stack of a coal-fired power plant. What is the problem there? Plenty of CO2 and nitrogen and oxygen and SOx and NOx comes out from there, and it goes to the atmosphere. I don't want that carbon dioxide to go to the atmosphere. Why you don't want? We will talk about it later. But at this moment, we don't want this CO2 to go into the atmosphere. So what we are trying to propose? We are trying to propose that we will capture the CO2 part of the other gases in this gas mixture. Nitrogen and oxygen we will release to the atmosphere because that does not bother us. The CO2 is bothering us, so we will capture it, we will store it, and we will see what we have to do with that. Okay, so this is one of the application here talked about. So what I am saying, if I have a mixture of CO2 and hydrogen or CO2 nitrogen, I pass it on into a reactor which is only having water, nothing else. Okay, nothing else other than water. If I have to otherwise capture CO2, I will have to have a geolite, I will have to have a metal organic framework, I will have to covalent organic framework, I will have to have some amine, I will have to have some alcohol, something I will have to have. But all of these, please understand, has to be synthesized. Humans will have to synthesize it. Okay. In this particular case, I am saying we don't need to synthesize anything. We'll just use water. Okay. Now, if I am using water, if I am going to the right temperature and pressure conditions, what will happen? These two gases, out of these two gases, one gas, what is my challenge? I have to ensure only one of the gas goes into the hydrate phase, the other should not go. This is where I will basically do my research. How do I ensure that only carbon dioxide should go into the hydrate phase and nitrogen or hydrogen or any other gas which is there should not go? If I am able to achieve it, what I have achieved? I have been able to get a gas phase which is not having any carbon dioxide, and I am going to have a solid phase which is only having carbon dioxide. Now, technically, theoretically, it should be possible, but it's a physical process, it's not a chemical process. What is the difference between a physical process and a chemical process? Physical process cannot be polishing process. It basically means that you cannot get accurate, that 99.99% will be like this. It's only true in chemical process, because there is a new entity which forms. So, you can convert completely anything into something else, but a physical process does not do that way. So, if there are 9 molecules of CO2 will go in there, or if 90 molecules of CO2 will go in there, 1 molecule of hydrogen will also go in there. You cannot stop it because it's a physical process. There is no binding, okay, they are just interacting. So, there will be strong interaction between CO2 and the cages around it, but then there will be some hydrogen also which will go in there. The location is there, the vacancy is there, it will go and fit in there. Who will stop it? Okay. Hydrogen may have higher fluctuation, but at any given point of time, one hydrogen molecule will behave in such a way that the fluctuation will be less, it will get trapped into the cage, and once it has trapped, it is trapped. Okay. So, this process is good for large scale implementation, may not be very good for polishing something. Okay. It basically means if I am going to have a large system where I want to capture 90% of it, 80% of it, 70% of it, I should be able to use it. That basically means that this will work for large scale. We will talk about it maybe in little detail later. So, we do, as an engineer, we do energy analysis, we do the capacity. For example, chemists also look into this millimole per gram. So, we see that there is some 7 to 8 millimole per gram capture capacity, which is pretty good actually. If you look into the best metal organic framework and this kind of temperature, you will see around 4 to 5 millimole per gram. So, it basically means I am not using a material, I am using just water, and I am still able to do 7 to 8 millimole per gram. So, that is a very good number, but then it is only millimole per gram. This is where the difference between a chemist and an engineer come. When an engineer will look at this data, they will say it is of no use to me. Why? There is no time here. I need data which should be saying millimole per gram per second, because this millimole per gram might happen in second, it may happen in hour, it may happen in a day, who knows. How do I design? Okay, unless and until I have the time there, I cannot design any reactor. No, I need to design, it should be 100 liter reactor, it should be 1000 liter reactor. How do I design if I only get this data?
You're saying the reactor contains water and you're passing a mixture of carbon dioxide and hydrogen. But then that cage is forming on the basis of the molecular size of the carbon dioxide and water, or like they're already there?
Nothing there.
How can we differentiate that? If the cavity is more, then CO2 can occupy. If the cavity is smaller than hydrogen.
I am coming there. That is where I will go. Don't worry. I see, this is where I am different from others. I don't go to the depth first. I go to the shallow part and then we will go to the depth. Okay. I want you to first understand the application. Remaining things we will talk about. You see, too many calls nowadays. Okay. So, very important point, and I want all of you to ask questions, because this is this workshop or this kind of a school is important to interact. Okay. I am not here to present and be done with that. Okay. Even if I will not finish everything, I will not mind, but whatever I finish, you should understand. That is the point I am trying to make. Okay. So, very important point, but we will come to that. All of this is done. Let us move to the next slide. In this particular case, I just want you to understand this. This is a physical process. It basically means if I have lesser amount of CO2 in my mixture, and if I have to get 100% CO2 or 99% CO2, I will have to do this step multiple times. It is not a chemical process. If it is a chemical process, what will happen? CO2 will react, will form something else. So, there will be no CO2 left. I will get only pure nitrogen. I had warned you guys that this is a physical process. It basically means that if I am bringing it this particular process, it basically means I cannot talk about 100% purity. Why we do this? Let me explain that. That is more important. Why do we do this? We do this mainly because if I am using a chemical process, what I will have to do? I will have to bring another chemical which will react with CO2 and will form something. So, we are talking about a reaction. What is the reaction we are talking about? Let us say carbon dioxide is A. Okay. The other chemical which we brought is B. Okay. So A and A prime is mixed together. A prime is nitrogen, A is CO2. What I am trying to do, I am trying to separate A from a mixture of A and A prime. Okay. So what I am saying, I am bringing a molecule B which chemically reacts with A. So what will happen? A will react with B and form C. Fine. As soon as A and B will react and form C, we know that A prime and C will not react. For example, if I have taken an example of CO2 and nitrogen, if I bring nitrogen to any chemical, do you think it will react automatically? Most of you do your experiment in nitrogen environment, no? Why do we do it? It does not react. Okay. So in this particular case, I am trying to separate CO2 and nitrogen. So we bring a molecule B which will react with A and will form C. I have separated. What is next? If I have to separate, I have to keep bringing C. Where I will keep bringing C? This is a man-made material C. So we cannot have infinite source of C. Carbon is coming from under the earth, which is why it is infinite source. I am digging the coal and the oil and burning, so it's an infinite source. But the C which I have used to capture this A is not an infinite source. What will be this C? Typically, I don't know, many of you may not know, amines are used for this kind of work. Amines are basic in nature. CO2 is acidic in nature. So what do? You bring an acid and base, it will form a salt. Okay, that's how you separate it. This is how what is a commercial process looks like. It's not very rocket science in there. You bring a base, you react it with an acid, and it will form a salt which will come out of it. So you have captured it. But the challenge comes, you have to regenerate that material. Okay, because if I don't regenerate this C, I cannot have an infinite supply of C. I need some C every time for this capture to happen. This is why we don't go for a chemical process always. Because if I am going to see a molecule which likes each other so much, if I have to break it apart, I will have to supply more energy. Okay, this is why chemical processes are not always your process of choice. You want it to be interacting sufficiently enough that it can get separated out, and when I want to regenerate, I supply some energy, it will go out apart from each other. So basically, this is in simpler term, we are looking for girlfriends and boyfriends. We are not looking to marry each other. You understand? If you marrying, it basically means you will have only option left is divorce. Okay, it basically means you will have to supply a lot more energy for you to basically separate them out. So most of the processes in this case, which is a cycle process, you look for physical interaction just close enough, they are not married yet. When there is no match, they will just move out. They will not bother about it. Okay. So that is how you basically do this kind of processes. So it's an engineering approach. You have to look for the entire cycle. You cannot look for one process. One process might look better, but you look at the reverse and you see it's not working. Okay. So this is something which you have to always worry about. So coming back to your question, if you see, I think there was one more. Okay, maybe in this slide. Yes. Look at this data. You have pure nitrogen which forms hydrate at this kind of pressure. The first thing we look at is thermodynamics, okay? And you have pure carbon dioxide which forms hydrate at this pressure. So if I am at 280 Kelvin, the pressure required is roughly 20-30 bar. But if I am at same temperature for nitrogen, I need some 300 bar for hydrate to form. So now if I have a mixture of these two gases and when I form hydrate, what will happen? Yes. So if I am at somewhere in between, somewhere over here, then when I am forming hydrate, primarily CO2 will form the hydrate because it has lesser thermal fluctuation. It's all about, it's a net where it has to just go and sit there. So if you have lot of energy, you will resist to go in there, or even if you go in there, you will come out of it. But if you have lesser amount of energy, then you will go in there, you will not have enough energy to come out of it. This is what we are trying to do over here. I have identified the right temperature and pressure conditions where I know CO2 will go into the cage, but nitrogen, even if it goes, it will come out. Okay, this is one. There are more. This is not that simple. Okay, so we will talk about it in the next slide. So, but what is shown over here, you see there are different kind of hydrates which form. And you are right, that it depends on the size of the guest molecule. For example, if I have one molecule which is of this size, if I have to wrap around this molecule and I know the hydrogen bond length is going to remain the same, it can't change too much, no, at certain temperature. So, if this is the length of a hydrogen bond, if I have to wrap around it, how many molecules will be needed? Let us say there are these 6 molecules would be needed. Now, assume this molecule is not this size, this molecule is this size. Do you think only 6 molecules will be able to wrap it around? No, no, it basically means the cage size will depend on the size of the guest molecule. Okay, so it basically means that depending upon the size of the guest molecule, I am going to have different structures. There is one, you see here the large cage, it says there is 12 pentagon and 2 hexagon. Okay, then you have another cage, large cage, this you say 12 pentagon and 4 hexagon. Then another large cage, you see here there is 12 pentagon and 8 hexagons. So, depending upon the size of the guest molecule, you see different structure forms. One common cage is there which is 12 pentagon. In this particular case, there is one other middle cage also, this is some other odd shaped cage. It basically, if you look into this, there are more details into it. I do not want to go and I can't teach you everything on hydrates about it, do not worry about that. The other details are there, you see here, in this unit cell, you see there are 46 water molecules, okay, and 2x and 6z basically tells you there are 6 numbers of large cages and 2 numbers of small cages. So, there are 46 molecules, water molecules, which form 6 large cages and 2 small cages. So, you now look at the ratio 3 times 3 is to 1. Now, if you look into a structure 2, you see there are 136 water molecules where there are 16 small and 8 large cages. The ratio is 2 is to 1, small to large. So, lot of details are there, not only the temperature and pressure condition which will determine what a structure is forming, also what kind of size and shape is there and what kind of a structure form. It is easier for a single guest, but when you have multiple guests, then it is a complex process. Okay, we will talk about it maybe in the next slide. Is that clear? Whatever little I was able to explain, I have explained, but if you want more details, you can ask me. If you ask me a question, I will handle it. Now, if you look into having a mixture of carbon dioxide and nitrogen, CO2 is something like this compared to nitrogen, which is this small. Okay. Now, I am forming a hydrate of CO2 and nitrogen. CO2 being larger in size will have to fit at least over here in the large cases of structure 1 hydrate. So, typically methane and CO2 forms a structure 1 hydrate. It basically means the size of the guest is such that it can fit into the large cage of the structure 1 and possibly it also fits into the small cages of a structure 1. When we form such hydrates and we do an spectroscopic analysis, we have seen, and this has been proven multiple times, that when a structure 1 hydrate forms with methane or with CO2, let us talk about methane first. If it forms with methane, all the large cages has one methane molecule in it, typical temperature and pressure conditions of Earth. Okay. If I am going to some other planet and we are going to gigapascal range, then more methane molecule can go into one cage, but we are not talking about that here. I do not want to go that deep, that will complicate things further. But typical kind of pressure we see on Earth up to 100 bar, 200 bar kind of pressure, you will see one methane molecule will be present in all the large cages of a structure 1 hydrate, and roughly 80% of small cages will have methane in it. Now, 80% means it is a function of time and it is a function of pressure. If I wait for longer time, more methane can go into the small cages, but maximum 80% has been seen. It basically means if I am doing at a very small time analysis when a hydrate crystal forms of methane hydrate, possibility the amount of methane in the small cage will be lower, because I have not given them enough time to basically interact. So, some cages might remain vacant, it might still be stable, but remain vacant. If I am going to give it lot more time, if I am waiting 1 year, 2 years, 10 years at the same pressure condition, we have given enough time for methane to diffuse through to the small cages. So, in that particular case, more methane might be present in the small cages, but we have seen natural samples which basically mean millions of years, and we have seen maximum 80% of the small cages are occupied by methane. But the same study when you do with carbon dioxide, you see that large number of all the large cages are occupied, but only 40 to 60% of the small cages gets occupied. Why it happens? Because CO2 is slightly bigger in size compared to methane if you talk about the van der Waals radius. Okay. So, in that case, it is very clear that CO2 being larger in size does not fit into this case. But let us not digress. These are all digression. What we were talking about, we wanted to have a separation. How do I separate it? So, now when I am mixing CO2 and nitrogen together and trying to form a hydrate, nitrogen being smaller, now I think this is something which I have to tell you before. Now, methane and CO2 is bigger in size, nitrogen is smaller. So, when nitrogen is small in size, which structure should form, a structure 1 or a structure 2? So, let us look at it. So, when methane is bigger and nitrogen is smaller, it basically means nitrogen can go in this case as well as this case. Okay, because 80% of the methane I was able to fit in this cage. Now I am taking a smaller molecule. It basically means it will go in this cage as well as in this cage. But then if that is true, it is also true in this structure. It can, because the larger cage is even bigger than this and the smaller cage is as big as this. So it might be true for this as well. So where it should form, whether it should form a structure 1 or a structure 2? Someone said a structure 2, why? Why? That's what thermodynamics. If you look, I forget about this thermodynamics. I don't know anything about thermodynamics. Just looking at this, is there a possibility for you to figure that out? Entropy driven, certainly. But anything more? See, in this case, I was telling you there are 3 times as many large cages compared to the small cage. In this case, there are 16 small and at large, twice as many small cages compared to large cage. So, when a molecule is small, it prefers a small cage. So, it forms a structure 2 hydrate. Okay, but when it forms a structure 2 hydrate, it forms at a higher pressure. So, a molecule which is smaller than methane will form a structure 2 hydrate, but it will form at a higher pressure than what a molecule like methane or CO2 can form at any given temperature. Okay, so at a given temperature of 280 Kelvin, we talked about CO2 forming at around 30 bar, and at 280 Kelvin, nitrogen forming at 300 bar. But then that 300 bar, it forms a structure 2 hydrate, structure 1 it never forms. Okay, that is one information. The second information, if I have a larger molecule than methane, what will happen? What do you think will happen? If I have a larger molecule than methane, it will form structure 2 because it has a bigger cage. Large molecule cannot fit into this small cage, large cage of a structure 1. So, it has to form structure 2. Now, when that happens, what will happen to the small cages? Because it's too big to fit in the small cages, all the small cage remains empty. Okay, this gives you a stable hydrate at a much lower pressure, but then all the small cages are empty. Now, when you are a chemistry person, you don't bother about it, but when you are an engineer, you need to bother about it. When this remains empty, what will happen if it start dissociating? That is what will come to my mind. What do I want? I want it to form as well as dissociate. So, if my majority of the cages are empty, I will be able to ensure that it dissociates faster. Because if I am going to use it for an application in industry, I want kinetics to be really fast. It should happen in a minute, should not take 1 hour. Okay. So, this is something which we will have to basically understand. These are the ways we basically look, our solution should fit into that industry. Fundamentally, how I have to tune it so that it meets your requirement. This is what we basically have to always do. Too much of details, I do not want you to go into all of these details, because I am sure you are not a person who wants to work on gas hydrate. But the point I was trying to make, for example, I will give you another example. Now, if other option for me would be that I want to separate a carbon dioxide and nitrogen mixture, and I think little bit more. I say, okay, fine, I will add another molecule into this gas mixture or in liquid water, and so that it packs all my large cages. For example, there are liquid hydrate formers, tetrahydrofuron, cyclopentane and all. What I do, if I can use that, which is THF, is a very soluble molecule in water, is 100% soluble. So when I put some little amount of THF in water, it forms hydrate at very high temperature. I can form it even at room temperature. Okay, what I have achieved now, you see, if I have packed all my large cages with THF molecule, and if I am supplying a mixture of CO2 and nitrogen, CO2 does not like to fit into the small cages, only nitrogen will fit into the small cages, and I will be able to separate it. Okay, so these are the tweaks which I will have to now do to use this for my own application. Okay, and then there is a structure H hydrate. In a structure H hydrate, you need, all of these may form only by a single gas. Propane alone, even it does not fit into the small cage, will form a structure 2 hydrate. CO2 alone will form a structure 1 hydrate because it goes into both the cases. Methane alone will form a structure 1. Ethylene oxide will form a structure 1. You name a gas, it will form a structure 1. Nitrogen will form a structure 2 hydrate because it will go into large as well as a small cages, but it goes to a higher pressure. Why do we need high pressure? Because nitrogen, if it is going into the large cage, requires to be contained, otherwise it will come out. Okay, this is why it forms a structure 2 hydrate at a higher pressure. If I have to do it at low pressure, I gave you a solution. I will add an additive like THF or something like that, which will form a stable hydrate, and I have all my empty cages empty, small cages empty, where I will preferentially put one molecule of my kind which I need to be separated out. Okay, that's how I will separate it out. In this particular case though, minimum 2 guest molecules, 2 types of guest molecules are needed. One large molecule, very large molecule, and then a small molecule. Why? If you look into this, you see, in this particular case, if all the large cages are occupied and small cages are empty, the ratio of large to small is 3:1. It means majority of my cages are occupied. This is stable. In this case, if I am having all my large cages being occupied and small cages being unoccupied, because propane like molecules will not fit into the small cage, the ratio of large to small is 0.5. In this case, you see the ratio of large to small is 1/5. 3 small cage, 2 medium cage, 1. So that is too small a number of molecules occupying a cage. So this structure H hydrate is not stable only with one molecule. Okay, because there are plenty of cages which are empty, because a large molecule cannot fit into these cages. So it will remain empty. So when majority of your cages are empty, it will collapse. It will not give you a stable hydrate. So this is why a stable structure hydrate forms only when I have another guest molecule which can stabilize the small and medium cages. Okay, so 2 different types of molecules are needed for a structure H to form. So when we did one such a study, we saw that when I am going to we want to separate a mixture of carbon dioxide and methane. We didn't talk about CO2 methane yet. We talked about CO2 nitrogen, CO2 and hydrogen. There are 2 different sizes. Easier. When I talk about CO2 and methane, which both forms a structure 1 hydrate, how do I separate it? It's complex. This is where you will have to basically go a little bit more deeper. You have to do analyze hydrates at different things and all. And this is something which is published already. So I don't want to bother you guys with all of that. But this is only the thermodynamic part. Now comes the kinetics. Why? Because lot of CO2 will be coming out from any power plant. I need to have that rate at which it can be converted. So then we look into the kinetics of it. So you see here there is a water column and there is a gas column, and this is a gas which is CO2 and water column is H2O. And then when you do an experiment, you will see that sooner than later there will be a growth of hydrate and your reactor will be filled with ice like crystals, which is actually not ice but hydrates, because your temperature is 1.5 degrees. At 1.5 degrees you cannot form ice. Okay, and if you are seeing it, it basically means, now if you look into this 1200 second, hardly 20% of water got converted into hydrate. I can do those calculations, how much water got converted into hydrate. If I do this, I will not be able to scale it up. I need it to be much faster. Instead of 1200 second, 20% conversion I should achieve in a second. This is where we need to basically look at on kind of additives which will go in there, which will enhance the rate of hydrate growth. So those things we do, you see in this particular case, this is the kind of hydrates we see, and it happens in a second. In a second you will see all your entire water will get converted into hydrate. By doing this, what we have been able to achieve? By doing this, we are saying that if I can do through in stir tank reactor, this is the rate at which it is forming. If I can do in some of my packing and all, so there are two things which comes into picture. I want, if water and gas has to be brought together, how do you bring these two guys together? Water, what is the solubility of methane or CO2 in water? Do you know, any of you have any idea what is the typical solubility? 1 in 1000 maximum. At high pressure, 1 molecule of CO2 and 1000 molecules of water will be there. That is the solubility limit. When we talk about methane, 1 molecule of water and 100,000 molecules of water. The solubility of methane is so poor. Okay, so when we talk about CO2, now please imagine a scenario where I have presented that I don't want to use any material, I will just convert water into hydrate and I will separate this gas. Easier said than done. Why? Because I have a liquid phase and I have to supply gas phase into this liquid phase. They don't mix with each other. How do I do it? I'll have to stir, but a stirring can happen in lab scale, 100 ml, 200 ml, 1 liter. If my reactor is 10,000 liter, how do I do stirring? Can I do stirring? Not possible for me to do stirring. It basically means the gas and liquid will not come together. Why it has to come together? You see, the other thing which you missed here, which I probably didn't talk about, is this. If I am forming a hydrate of CO2, how many water molecules are there? 46 water molecules are there. And how many guest molecules are there? 6 molecules in the large case and at least 1 molecule in the small case, roughly 50% occupied. So you see, what is the ratio? 45 by 7 or 46 by 7. What is the ratio we talk about here? Roughly 1 by 7. It basically means every 1 CO2 molecule is surrounded by 7 water molecules. What are we trying to achieve here? The solubility of water, CO2 in water is for every, at very high pressure also, for every 1 CO2 molecule there is 1000 water molecule. How much is needed? 7. So it basically means I have to increase the concentration of CO2 in this media 7 times, 10 times, 30 times. Then only I will be able to achieve the faster rate, otherwise it will not possible. Because if I just imagine a reactor where I have supplied some gas via stirring, at some corner hydrates are growing. But what will happen when hydrates grow? It requires CO2, no? What is the ratio of CO2 and hydrate? Only 1 molecule of CO2 in 1000 molecules of water. So once 7 molecules of water comes together to in case this CO2 molecule, I need more CO2 molecule, then only the rate will increase. Otherwise, how it will increase? The raw material itself is not there. This becomes a challenge. Okay. So this is why the kinetics comes into picture. How do you enhance the kinetics of these hydrate is what the focus is on. So instead of doing a stir tank reactor, I will distribute the water on a packing. Okay. So that I use the packing. Now, I also told you that hydrate growth is an exothermic phenomena. It basically means if I don't remove the heat, temperature will go up. So, you saw the phase diagram. If temperature goes up, hydrate will not form. That also I don't want. So, this is why I have to have a packing which will distribute the water. The packing should have a very high thermal conductivity. So, all of these things you don't look into when you do it from a chemistry point of view, because it is an application. You need to understand the requirement of the application and then you will be able to basically talk about it. Fine, lot of things goes. So when I can do a packing, I can do sand, I can do silica gel. So you basically, I see not much time is left, so I will go little fast. So we do lot of these. How do I understand how hydrate will form? So we can do MRI. We can understand where the CO2 molecules are going, how the water molecules are getting converted into hydrates. So all of those things are there. We can do lot of MD simulation, what kind of additives would be needed for our water to basically come together faster, or molecules to basically get encased, or how the molecules when it start dissociating, it will be able to dissociate faster. For example, I'll give an example. I have a large chunk of solid hydrate. Let's say I have somehow ensure that hydrates are started dissociating. So when hydrate starts dissociating, what happens? Temperature goes down. And methane molecule, let's say it's methane hydrate. So methane molecules are still around that hydrate when it has dissociated. So when it's still around and when the temperature goes down, it will reform. Okay. What do I need? I need the CO2 molecules to be pulled out from there as soon as it dissociates. How do I do that? You can have an additive which will preferentially interact with methane molecule and will pull it out from there. Okay, in a liquid solution, I put an additive which has a preferential interaction with an hydrophobic molecule like methane. So as soon as it dissociates from water hydrate, anyway it does not like water, it wants to be away, but there is no physical possibility for methane to go out. So I have an additive which will attract this methane molecule towards it. So it will come out. Once it comes out, the next methane molecule will come out. If it does not come out, then this methane molecule will not come out, because the chemical potential difference for the methane molecule depends on how many methane molecules are around it. If it sees no methane molecule on the other side, it would think that, okay, let me jump out of it. But if there are all methane molecules all around, it will get tricked into believing that I should stay here. There is no point in me moving to the other side. So this is how it basically works. So you need to worry about all of that. So ultimately you can basically design some of this process. So this process was designed, and what happens, a gas mixture comes in, and then by the time it goes out, it's not pure but 99% pure, 98% pure, 95% pure. You should be able to basically get. You see, this is the kind of hydrates which grow over here, and ultimately you can basically scale it up. You can do this kind of studies and say that I have been able to come to a process of carbon dioxide capture. There are a lot of other details, but these are CO2 sequestration. I don't think we have time to discuss all of these. We have many other processes which we develop in the lab. For example, this is one process which captures CO2 directly from the air. This is not hydrate based though. This is a chemical process, okay, where you can basically have a room full of all your data. This particular room is supplied by a known concentration of CO2 24/7, and then you demonstrate how do you capture the CO2 from this. Okay, so all of these are there. We develop larger scale pilot plants to basically separate carbon dioxide coming out from flue gas stacks. Okay, there are 10% CO2, 90% nitrogen and all. So we ultimately start everything from the fundamentals. Slowly you get one step at a time, you go to the larger scale. You develop this at lab scale, then you go to the larger scale, you understand something over there. So all of these are step by step, but everything starts from the same chemistry. If I don't have a right molecule, nothing of this will be possible. Okay. We do a lot of this. Is water purification we talked about. This is a water purification unit which we have delivered to one industry. The demo unit for the phase change material, we talked about the refrigeration process. Okay, we have demonstrated that unit also. So we move on to last 5 minutes. I want to tell you guys the challenge of kinetics, which I know people typically don't bother too much about in chemistry. Okay, we will go to that particular slide, which will, yeah, this is the slide which we are talking about. I know I'm little clumsy here and there moving, but the point is that I want to focus on the things which is more important than just saying something. See, when we talk about this kind of presentation, we don't really focus on, there are two type of research. Now let me focus on the aspect. There are two type of research. One research which is done at fundamental level. Okay, it potentially goes to very high impact journal. But then if you think that that will allow you to translate it, that's fancy thinking. Okay, it's a very different kind of research. This is a research which are played in a different domain. Okay, the research which ultimately gets translated is a very different domain. Okay, when we do this kind of research, which typically go to the publication and all, we don't really bother about the scale up, the kinetics of the process. We focus mostly on the thermodynamics and the science behind it. Okay, we develop the material. But when this material has to go for actual application, there is a big gap. Okay, that gap not necessarily you can fill right away. But what I want you guys to think always in that kind of way, because ultimately whatever you are developing has to go for some application. If that application is not possible, you may develop a lot of processes, it will get published, I am telling you, Angawante Chemi and Jax and all will come out. But if you really want it to be getting applied in reality, then you have to always think about the scale. And this is what I will tell you, what is the point I was trying to make so all this while for about kinetics. And this is something which chemistry students should never forget about, is the scale, okay, because you don't talk about the scale. Now let me tell you carbon dioxide capture. I'm sure all of you would have heard about carbon dioxide capture. Net zero, many of you would have heard about. Today I'm not giving a net zero talk, but typically we know that we need to, one of the way to achieve net zero is by capturing carbon dioxide, utilizing it or sequestering it. Lot of research is happening. Anyone you ask, many faculties in chemistry department or anywhere, they'll say, I work on carbon dioxide capture. Good. What do? I work on metallurgy framework, I capture the material. Very good. But then think little bit beyond that, and this is what I want to focus in next few minutes. See, why we need to, when we say we are working on CO2 capture, where it will go? It will have to capture CO2 from a power plant, where a coal is burnt every second, every day, and supposed to produce electricity. So should not we look at from that side and go reverse engineering and see what do I need to do? Okay, so let's look at from the other side of it, not from this side of it that I am working on CO2 capture material. Let's look at what is needed. So once we know what is needed, then I will be able to tweak our process so that I will ensure that what is needed I will be able to deliver. Okay. So typical electricity generation unit, which is coal fired power plant, are 500 megawatt units. Okay. In a power plant, let's say, I'm not sure any of you know any power plant in your region. Anyone of you come from some power plant region where there are power plants, coal fired power plants? How come? It's not possible. NTPC, which NTPC? Let's say Ghaziabad or some place. So there is one NTPC. Singrauli. Okay, you come from that location, I come from that location. This is what I'm saying. Yes. So there in near Singrauli, there is a place called Bindhanagar. Okay, there is a power plant which is called Vindhyachal Super Thermal Power Plant, VSTPP. Okay. So this VSTPP, this unit is the largest power producing unit in this country. Produces roughly 3000 megawatt of electricity. It basically means that they might have 6 such 500 megawatt units. Okay. Now let's try to see if I have to capture CO2 from one of my real application, where the challenge would start from. So a 500 megawatt capacity emits 500 tons of carbon dioxide per hour. How much? 500 tons. 500 into 1000 kilogram. Okay. So 500 tons of carbon dioxide per hour is roughly 12,000 per day. 12,000 tons per day and 0.15 tons per second. Now this is the data which I have given you, which is a real data. Fine. I am going to capture CO2 from this. This is the real requirement. If I am doing something else, does not matter. If I am developing something, it should go there. So now let's look into the information. Now this is CO2 content. The flue gas is roughly 10 to 15% CO2, remaining is nitrogen and oxygen. So what is the flow of the flue gas? 96,000 ton per day. From one of the 6 units from this in power plant. Okay. Now you see 96,000 per day of flue gas has to be treated. If I am talking about CO2 capture, this is my challenge. 96,000 per day of flue gas from one of the unit has to be treated. Now let's go a little deeper. The best material which has been found suitable, which captures 4 to 5 millimole of carbon dioxide per gram of material. You see, as soon as you come to the lab, it comes into millimoles. 4 to 5 millimoles of carbon dioxide can be captured in 1 gram of material. But that is not sufficient for me, because I was telling you that I need the second data, because as you see, the first thing I say per second. If there is no second data in your data, how do I use it? I can't use it, no, because you might say that I will capture 4 to 5 millimole carbon dioxide per gram, but you will do it in a day. You may do it in an hour, you may do it in a second. How do I know what you have done? So this is why you look deeper in, whenever you generate this data, please generate with time. Okay. So now also the best material. So now we dig deeper into the literature and we find that instead of 4 to 5 millimole of CO2 per gram, I have a better data in literature which says 0.2 millimole of CO2 per gram of material per second. So I convert 0.2 moles into gram. 44 is the molecular weight. So 0.2 into 44 become 0.0088. So I wrote it at 0.009. So now what is my problem is now little simpler. I know the capacity in second. 0.009 gram of CO2 per gram of material per second. But this is too small. How much I need? I need it in tons. So I'll have to convert this gram into ton. So I have converted this gram into ton, and this gram also becomes ton. So ton, whatever unit I put here or here does not matter if both are ton and ton. I leave the second as second. Simple, everyone understands it. So now my problem is that I need to do, I know my capacity of material is 0.009 tons of CO2 per tons of material per second. Now the question is that how much gas I have? 0.15 ton per second. So I do the math, I see roughly 16 tons of material will be needed to capture the CO2 coming out every second from this plant. How much I need? 16 ton. But I did a mistake. What mistake I have done? See, when you do an experiment in the lab which is in milligram, microgram, every molecule will be see a carbon dioxide molecule. So the kinetics will be fast, thermodynamic capacity will also be better. But when I convert that gram into ton, it will not be the same. Instead of powder, I will have to pelletize it. The depth of the pellet, I will not see any CO2 molecule going. Typically, the thumb rule says that if you scale it up at that large scale, the kinetics drop will be 10 times. Thermodynamic drop will be 10 times. I am not assuming 10 times, let us say only half. Okay, what does that mean now? That means if my kinetics and thermodynamics goes half, instead of 16 ton of material, I would need 32 tons of material. Okay, and instead of 1 second, it will do it in 2 seconds. Simple, easy. I am trying to make it so simple that everyone understands it. So now what is my challenge? My challenge is that I will have to have a 32 ton of this material to capture this material. Now, if I have 32 tons, I will have to pack it in some reactor. No, 32 tons of material has to be packed. So 32 tons of material, let's assume the density is similar to water, 1 gram is 1 centimeter cube. So how much will be that? 32 meter by 32 meter by 32 meter. Yes, I know that, I am seeing that. So 32 meter by 32 meter by 32 meter. Now I need a reactor which is 32 meter long, 32 meter wide, that I am able to manage. How you will manage a 32 meter height reactor? It basically means I will have to break that 32 meter height into probably 3200 small units. So you imagine the scale. Now this is only half the story. Why? Because I needed 1 second of residence time. Here it is doing it in 2 seconds. Basically means I will capture only 50% of my material. Remaining 50% will come out without captured. So to capture 50% of my material, I'll have to do this. How you will pack it? You understand the challenge? You have designed the material, you have done, and so what is needed? Now there are many other problems which I have not even talked about. For example, this 32 tons of material which you have created, what I am doing, I am capturing carbon dioxide. This 32 material has been created, no 32 tons. When you create some material, how much CO2 you will emit? You will use the same energy to create that material. So that also gets added there. And you will have to regenerate it, because every second you cannot create 32 tons. So you will have to regenerate it. Regenerate basically means you need another unit of 32 ton next to it. So while this is capturing, this is getting regenerated, and when this gets regenerated, this will capture and this will get regenerated. Then only you will make it continuous, otherwise how you will make it continuous? See the challenge. So if you don't look at from the user point of view, your science will not really make a difference. So this is why you see I went in the wrong direction. Instead of starting from fundamentals, I went from the application. This is why I always go to application first. You have to first understand where I will be, whatever I am doing, where it will be utilized. That's the first question you should be asking. Because if you are not thinking there, you can do hundreds of new discoveries over here, but that will never get affected. And you will always be told that, oh, you people are academic people, you only do things for papers. Whatever you do does not get applied in reality, because you have to start thinking from their side. If you don't start thinking from their side, then whatever you do, you might fail. In this classic case, it will be difficult. Okay. So with this I will stop. I know that I have taken lot of time. There are a lot of other things which I can talk about, but I don't have enough time.